Hey, this is Steven from Legit Tech Tutorials, and welcome back to my Dyno DIY Dyno videos. I should be working on my water jet project, but I really love doing these Dyno videos, and also I'm sick right now, trying to get over being sick. So I have been, I'm taking the gym off this week, except for maybe Friday, so most of the week, and then so I have quite a bit more time. 8:30, usually in an hour and a half, I'd be heading to the gym, but now I feel pretty good. So have my tea here with some honey in it, cinnamon tea. So if my throat gets really bad, I will take a sip of that, and that should fix most of it. Okay, so we're back working on the dyno. I made a mistake in the last video, which I believe, as far as my records show, is DIY Dyno 3. So this is DIY Dyno 4. I made an issue. I fixed it because I was struggling to not work on the project. And obviously, like I said, I do most of my stuff in video. So what I did is I just did OD times ID times length or something dumb here, which is not how you do density of a circle or a shell. So basically, the density of the shell is area OD, so pi, and you can see that SwiftCalcs has a built-in for pi. Pi times OD over 2 squared is area OD minus area ID equals pi times ID over 2 squared is area ID. And then area remaining is area OD, so if it was a cylinder, the outside area minus the inside area. So that's the leftover area is 0.005 meters cubed. And in here it looks like we have this pounds per gallon. The heck? Anyways, I probably should have changed that so it doesn't always say meters squared, so I don't have to keep converting it. Anyways, so yeah, area remaining, blah blah, is that. Is area OD minus area ID, mass is density times area remaining times the length, right? So density is, in this case, it was kilograms per meter squared or pounds per inch squared. Pounds per inch squared times inch, so that's inch cubed times pounds over inch cubed. Inch cubes cancel out, so this is pounds. So that's right. So basically what that lent to is that if we have two rollers, we actually had a 66 pound, so not like I showed before where it was like 400 pounds. So we're only at 66 pounds. So this brings up a good point. Usually what I do on these is not calculating there, so let me just refresh it. There it goes. So what I usually do on these videos, which I didn't do this time, is I didn't talk about the design criteria at the beginning. So I might have to do that. We might do that here, or maybe at the end of this video or something. Go on Trello and do a design criteria for this one. But basically, I want to be able to lift it and put it down. There's going to be two separate ones, so one per tire. So each one's going to have two drums, or we might change it to one drum, depending. So let's say we have two drums per, so total 4 drums, and there's 2 different assemblies, and you connect the 2 with a wire, right? And then the wire goes to the computer, and that way you can kind of check to see if the wheels are balanced or whatever. So basically it goes off of that. Those 2, or even there could not even be a sensor on one side, and you just measure one side over the other side. And if it's a car like my Rabbit, I think my Rabbit's only one side drive. It only drives on one side. It's unlocked. So with that, we could look at that and see, okay, which side is driving, and then attach the sensor from whatever side. And then just let the other side freewheel. But obviously we need both wheels, or we could just lift one side up off the ground, one wheel off the ground, and just have one carriage. But regardless, I want to have at least both sides to be able to be lifted and put down by one person, by just myself, let's say. So that being said, if it's under, I would prefer it being under 130 pounds each component. So what that means is that we could add a flywheel to this. So basically, we could get a big piece of steel, plate steel, like a 2-inch plate steel or something, at this place. Plasma out some of it, right? Take it to the shop, drill or do something, or attach something to it that I could use as a something to attach it to the lathe, and then kind of clean it up. Put it on the inside and clean it up. So that is something that we can add, because we can't really add a third roller. I mean, I guess we could add a third roller. That'd be kind of strange. I guess you would have to like be able to spread out the 3 rollers, and then it's 3 rollers, and then but the issue with that is that it drops the friction to each of the roller. It drops the weight per. And I'll have to do a diagram of that to check the actual normal force down on these parts here onto the wheel to see again how much force we could put down. So as you see here from the so what that means is that with that the mass being lower, we have 573 inch-pounds per, and we have 1,147 inch squared pounds for a dual roller. So that's obviously assuming that both wheels are contacting for that weight. Now, what we could look at as well is how long, so that was 15 inches, so how long can we get this until it's, so here that's 90 pounds. So if it's like 2 feet, then it would be, oh man, my tape measure is in my brother's room, but 2 feet, so I'm 6 feet. So me divided by 3. I think that's perfectly doable, and I think that'll be easier to carry. It's about shoulder width apart. A little bit bigger than shoulder width apart. So 2 feet, and that is 110 pounds. I think that is definitely doable there. And then we don't have to do some sort of 24. So we don't have to do some sort of dual, because the flywheel is going to be harder to machine than the cylinder, because the cylinder, you can just put the jaws of the lathe on the inside, and then do the outside, and then move to the outside and clean up the inside with a boring bar. Right, so it's way easier to do a cylinder than it is to do anything else. So with this, we have 107 with 2 rollers. Each roller is 54 pounds each. So that looks good. So 54 pounds each, and now we have 1,900 pounds. So instead of 1,050 or whatever, we have 1,900 pounds, 1,900 inch squared pounds. Okay, so again, I think so here's another question here that I wanted to look up. So let's go back and look at my history here on my other screen, and I want to look at that on that page yesterday. Show all history. Yesterday, I guess it might have been today. Technically, I don't know if it was 12 o'clock at night or not. I don't think it was 12 o'clock. There we go. I think this is it. Nope. Library history. So that's not it. contact table. Here we go. There it is. So now the other thing is what I could also do is I could also coat this. I could also coat it with rubber. I have some some seal from what is it? So either I could put like a Raptor bed liner in there, or I have some Rust-Oleum seal stuff for sealing. And with that, we might be able to. So here, dry rubber versus dry steel is 0.8. Interesting that greasy steel is the same number. I think these are extremely rounded, but anyways. So what about rubber? Dry rubber versus dry rubber. How's dry rubber versus dry rubber 0.8? Rubber versus, let's say rubber on rubber. Oh, this might be, oh, this is inside of the engineering toolbox. Rubber on rubber. Strange that they don't have. Oops. Rubber on rubber, clean and dry, 1.16. I know it could be over 1. It's interesting. Clean and dry. So it goes from 0.8, which, I mean, I don't know about that. Dry asphalt's 0.9. So yeah, it's probably around 0.8, I think would be kind of fair, I guess you could say. So we go from 0.8 to 1.16, but it's going to knock the thing out of balance, and it's going to add more weight to it. I mean, we calculate the weight, we calculate an average of the thickness, but it's going to knock our all of our variables off. But we could look at that as well. So here, let's do this. And if you double hit space, it goes spacebar. If you double hit spacebar, it goes into text mode. You see up here. So I'm going to say steel to rubber equals 0.80 static friction. Rubber to rubber equals 1.16. That's pretty good. 1.16. I'll leave it there. So let's change this to 1.16 and see what happens. So here, max friction force 408 foot-pounds. So now we're at 600. So we increased it by 2 times. Close to 2 times. So max torque is 542 foot-pounds. Now what I'm curious is if we could do the truck, my brother's truck. So my brother's truck is a diesel. It's a big diesel, and it is it's a Cummins 12 valve diesel, which I think is like 6,000 pounds. Let me see. So that's a 1997. It has a 2500, which I believe is a half ton. Gross axle weight, gross vehicle weight, rating, curb weight. Curb weight front is 2825. Curb weight rear is 2160. So together it's basically 5,000 pounds. 5,000 pounds divided by 4, right? Because this is going per side. So 5,000 pounds. Let's do this in calc. 5,000 pounds. 5,000. Oops. divided by 4, divided by 2. That's 625 pounds. Again, this is without any sort of being able to kind of put it at a different angle. So I think this one is frame gas. Okay, so diesel, 5.9 liter Cummins, 12 valve. Okay, so here it is. Bosch. So yeah, it gets, I think it's like, 144 horsepower or something. So 440 foot-pounds of torque at 1600, and it redlines at like 3, oh yeah, governed speed is 2700. Very, very low. So we see we have max friction force 730, and obviously the tires are bigger. The rim size, I don't know, I'm gonna have to look at the rim size, but the rim size is quite a bit bigger. This is up there, maybe 20-inch rims. So obviously tire thickness is way bigger too. Tire width is also like 240 or something, and these are like 70s or something, 1,000 foot-pounds. So with the truck, he'll definitely be able to do that. Obviously, we're going to have to... so I do like the idea of having the 2-drum, because we can... we could separate the load, so between 4 bearings instead of 2. We could have a bearing on each side, right? A bearing on each side for each roller, and it's separated between 2 rollers. But obviously, it's going to lower our friction, right? Because there's less weight on each side. So now it's split between 2 rollers. Thus, each bearing doesn't have to support 500 pounds, 600 pounds. Anyways, so yeah, so that's going to change quite a bit. So very, very interesting. All right, so now let's go ahead, and we're past halfway, running a little bit behind. Let's go ahead and use this equation that we were talking about. I equals omega plus angular velocity, which alpha is angular acceleration, is equal to torque. So now we know. So basically, what we know here is we're going to say here variables vehicle rated torque. Also, I was talking to my brother about this for motorcycles, and I think motorcycles, they have a decent sized tire. So even with my brother on the bike, so I think he has like a 400-pound bike. So let's say 400 divided by 2, 400 plus himself, that's 600 pounds, divided by 2 is 300 pounds. So let's say 300 pounds. And let's say that this is a 20-inch rim. I don't know, 40. This is like a 150 or something. 300, yeah, so even if this is smaller. Yeah, so this is way over what his bike only does, like 100 horsepower. So, and the torque is not nearly there. Okay, so cool. So this is torque. So you could also do a motorcycle with using one of those instead of 2. Use 1. So this is rated torque. I'm going to say 10, and let's do 1100. Because my dad just bought a 2019 diesel Ford with a 6.9 liter in it, and it's torque monster. So I'm curious if we could do that one as well. So foot, pound, force. Okay, now for the, let's say that this is the Mustang, 1965 Mustang, 289 C code. This is it. So here it's saying 1965 Mustang C code, torque 283 for the C code. It's probably somewhere in the A code range. might be 300. I'm gonna guess. So let's say 300. Okay, so vehicle rated torque. So we have torque entered in, and we have moment of inertia up here. So that's 2. We have system RP. We have angular velocity. So basically what we would have to do is we would have to do a derivative of angular velocity, because angular velocity is changing over time. Also, the torque is changing over time. Moment of inertia is staying the same, and angular acceleration is changing. So let's say we have equals angular acceleration. So let's say we solve for angular acceleration here. Because basically what I want to find out is how long this system is going to take to spin. So actually what we could do is I could go back in here and we could use that that calculator to figure it out for right now until I can figure out how to do it on my end. And maybe they might have something that we could see there that will tell us how they did that that math. So that was there it is. There's your Dyno sizer. Okay, so basically what we want to do is we want to get this guy to equal this other guy. So what we could look at is moment of inertia of standard Okay, so what we're going to use this guy here, moment of inertia, and then basically we're going to solve for this guy here of steel. And we're going to use the same A36. And so basically what we're going to do, I'm going to move this back so it's 1/2 mr squared. And we're basically going to solve for the outer diameter and the thickness. And then we're going to use that to kind of look at how fast this thing would accelerate using our vehicle with the rated horsepower. Also, so we should probably also do vehicle rated horsepower here as well. Okay, so but this equation right here is what we're going to use on the dyno. Is torque is equal to I alpha plus omega. Sorry. I don't know what the W is. Anyways, I don't know what the W is in Greek letter. So what we're going to do is we're going to put 2 sliders. We're going to say this is disk OD, and then this is thickness weight equals, or let's just say area disk equals disk is pi times disk OD divided by 2 squared. And then it's undefined, man. That's weird stuff. For some reason it doesn't like pi, and there's a lot of glitches there. Then weight, flywheel weight equals disk. Oh, this is disk area, not OD. Time disk area. Oops. Disk weight equals disk area times tire thickness. times times fly thickness. Okay, and then this disk OD, let's do this in inches. Okay, and then let's say that this is 20 inches and step size is in 0.1. And this is inches, and then this is like 10.1. And then this is disk inertia equals 0.5 times disk weight, times fly thickness times A36 density. Disk weight times radius disk OD. Oops. Squared. Okay, 1/2 mass times disk OD over 2 squared. Okay, so then we want disk inertia. Okay, so now basically what we need to do is we need to get this to equal that, basically. So let's go ahead and step down the OD. Oh, that's pretty freaking, oh. So let's drop this down to like 3 inches or something. Well, you have to do 1800, right? 1850. Okay, I'll call that good. So that is vehicle rate torque. That doesn't matter. Okay, so that's what we're looking for here. Disk OD of 12.2. Disk OD of 12.2. And thickness of 3 inches. Max horsepower, let's say it's the Rabbit, which is 53. Max flywheel RPM is 5,000, let's say. Oh, it's loading. Okay, so flywheel weight's about 99 pounds. It's 45.07 kilograms. Gear the dyno, keep flywheel, blah blah. So basically, with the Rabbit, it's going to be 1.88 speed. Oh, that's interesting to put two plates on the inside. I was thinking of it a little different. You need an acceleration time of 5 to 10 seconds. I agree. Okay. So that means that we are quite a bit off here. So what that means is, let's see what we actually need to get 5 to 10 seconds. I agree. The 7-second looked like it was pretty good. So let's see what we need here to do that. 13 seconds. Okay, 4-inch thick. How about that? $16. Thinking, sorry. Okay, so that's close. 16 by 4. So we need almost 7,000. So we need almost 3.5 times what we have right now. Now, so I do like this. This is pretty good. And we're at 30 minutes, but we'll keep going. Interesting. So they have a program here. No, I'm wondering if this is like something that you can use to communicate. Okay, so I'll read this probably off. Interesting. So yeah, here it is. Yeah, so here's the acceleration and then the downtime. So I think nowadays you don't need that big of an... Ooh. This is cool. These guys look like they're making pretty good software. I'll have to look at this. This is really, really nice. Let me bookmark this. Okay. This is nice, and also this is pretty good too. Okay, so that's 7 seconds. Now let's say that we have the other one, which is 1965 Mustang. C code is about horsepower is about, let's say, 225 probably right now or something. 1 second. So here it's saying it doesn't like the 16. And if we get this to go faster, then that's better. Wow. 500 pounds. Because really mass is not, you don't want to be messing with them. You don't really, this is basically just has to do with mass. Because it's 1/2 mr squared, so you're better off just increasing the diameter, really. So let's say that this is 5 inches, so 6 inches is pretty big. You're just kind of increasing the mass at that point. And 20. Okay, so let's say 21. So for the Mustang, you want 21 is, so it's like 20.5 or something, is the right thing that you want. 7 seconds. Okay, so 20.5 is 6. That's 26,000. So that's, so let's say that this is, oh, that's 27. Let's say, and let's say that this is 2. So that is 13.5 times more moment. So what I'm thinking is that we do these cylinders, and then we put a cap on the end, right? and we put the cap on the end, we can machine the cap flush with the drum, and then we can fill this thing with little caps on the inside. So basically we have this cylinder and we have a flywheel on the inside, flywheel on the inside, flywheel on the inside. So we cut this thing down, and then that will improve strength and also improve the strength of the bar going through, but we have to have these bearings that go in there, let's say. Unless we have some sort of bolt pattern or something so that we can take each piece out, press a bearing in or whatever, and then put it inside and bolt it down or something. I mean, basically we could have it where that rod is welded on. You push the rod in and you weld it on the outside, and then whatever happens on the inside is what happens. Or you could put the rod in, put the plate in, weld it, because that rod could clear right through the lathe. So you could make an inside piece, put it in there, weld it, put another piece in there, weld it, put another piece in there, weld it, and then just basically stack these things out. But obviously with a disc, you're going to massively increase the weight of the system, right? So the weight is going to go up faster than the moment of inertia. So the idea is we keep the thickness of those plates down to a minimum, and we just put more of them, pretty much. Just thinner, but more of them. So maybe like a half of inch thick, and just put a whole bunch of them in there. So that's one example. Now anything that has more horsepower than that is going to spin that stuff up way faster as well. So we'll look more into this later. I'm going to take a break and then film a different video. So this I might just do one today, and then we'll get back to it later on. Alright, thank you guys for watching my dyno video, and I'll see you guys in the next one. Take it easy. Peace.